Hello guys, in this lecture, I'm going to go over some examples that we had remaining on chapter 17, which is this guy, and a couple of other problems. So like I said last time, chapter 17 is all about realizing that on one figure we're going to put the forces and the moments, and on the other figure we're going to put MAG, and in addition we are also going to put IG alpha, right, where IG is the moment of inertia about the center of gravity. Obviously, before you do this lecture, make sure you have watched all the 3 lectures that we have on chapter 17, and then really understanding them. And then if you had questions on them, you can ask me, obviously, and I'll be more than happy to explain these to you. All right, so let us work on this chapter, on this problem, example 5. And in this example, basically, we have that spool, right, that is sitting on a truck. And the goal is the spool is basically constrained between these 2 blocks, B and then A. And I'm going to stop that so you can see the video very well. So we have this A and then B. And what we know is we would like to find the maximum acceleration of the truck so that this guy, the reaction here is going to be 0. Okay, so what the first step is we're going to do it by diagram, and the weight, guys, the weight will be at the centroid, right, or the center of gravity of the spool. And sometimes you actually put the weight on the air, right? Why? Because the center of gravity doesn't have to actually be on the actual material. How about the reactions on A and B? The reaction at B, we said the reaction is always going to be perpendicular to the tangent. And you guys know that the perpendicular to a tangent on a circle will always be pointing toward the radius, right? So that guy is your RB. And how about RA is going to be like that? Also RA we're going to assume to be 0. How about on here? We have MAG. How about IG alpha? Do we actually have IG alpha? No, we don't have any IG alpha, right, in this case. Because we assume that this at the verge of tipping, so there hasn't been any rotation yet. So at the verge of tipping, we're going to say alpha is 0, and at the verge of tipping about B, then RA is going to be 0, right? So this is what we have, and basically we know from the figure, and I encourage you right now, we want to obviously have the PDF of chapter 17 ready, and that is example 5. That moment arm right there is actually 0.3. Okay, and the outer radius, this outer radius from here to here is actually equal to 0.5. So what is the maximum acceleration that this guy could have? So it does basically lift off of this point, then we can sum the moments about B, right? Sum the moments about B. And we're not summing the moment about a point. Like I said, you never sum the moment about a point. You are summing the moment about an axis perpendicular to the figure passing through that point, right? So I'm going to use my counterclockwise as my direction. What is the moment of R for mg? It's going to be 0.3, right? So mg times 0.3, RA is going to be 0 in that case. The moment R for this vector will be 0 because it's actually traveling through this RB. And that guy on this end is going to be equal to MAG multiplied by, so now we need to know the moment arm for MAG. So this is point B. And I know that distance from here to here is 0.3. So this is the moment arm, which is L. And I know the outer of this guy is 0.5. So we know from Pythagorean 0.3, and then this guy has to be 0.4, or L is equal to square root of 0.5 squared minus 0.3 squared, which is equal to 0.4 multiplied by 0.4. So M and M will cancel out. So we know AG has to be equal to G multiplied by 0.3 over 0.4. So we get the maximum acceleration of the truck so that AG is, so that it actually lifts off of this point. The second part of this problem is we would actually like to find the reaction at B at that acceleration. And the easiest way here is to do what? So you sum the forces in this direction, in the X direction, and then if you sum the forces, what do you get? So we know MAG is horizontal, so basically we need to get RBX. So we can directly say RBX is equal to how much? MAG, right? Where the mass of this guy is going to be equal to how much? Okay, they said it has a mass M, so they don't give a value. So it's going to be equal to mg 0.3 over 0.4. How about the reaction at B in the y direction. So I'm going to sum the forces in the vertical. I'm going to call it RBY minus mg is equal to 0. So RBY is going to be equal to mg. And the actual value at RB, it's going to be square root of RBX squared plus RBY squared. All right, so this is the first problem. Okay, so let us look into another problem, basically, which is that problem here. And here we have, this is a lift truck, basically, which is lifting that spool. The truck, basically, the truck, which is this guy, the yellow part, has a mass of 70 kilograms. And the center of gravity for this guy is at G. We need to find the largest upward acceleration of the 120 kilogram spool so that the reaction on the wheels doesn't exceed 600 Newton, right? So these are the two wheels, and then this is that guy, right? And we need to find, like I said, the largest acceleration that he can give on this guy. So this guy is telescoping upward, right? This whole platform right there is going upward. And how do we solve that problem? Again, what do we do is basically we are going to do a free body diagram. I'm going to redraw it right now. So we have one wheel here, and then we have another wheel there. Okay, and this guy, these two wheels are connected like that, and then we have something coming up here, and then something kind of gets telescoping up and down, and then we are carrying a spool which is located over here, right? So the spool is actually, so we're gonna do a free body diagram on this guy, and we are also going to do a free body diagram on a spool, right? So the spool is gonna be applying a normal force N, let's say, and then I'm gonna say on the wheels I have two reactions, RA and RB, and then the center of gravity for the truck is at G. So I'm going to have big M multiplied by G, where big M is the mass of the truck. How about the free body diagram on? So every mass, guys, will have its own free body diagram and its own acceleration diagram. Does this guy have an acceleration diagram? No, it doesn't, right? Because this guy is not moving. What is actually moving is only the spool. So N will actually have an acceleration going upward. So what do we have? What is the free body diagram on the spool? So the spool actually has a weight mg, right? And then it has N, which is a reaction. So N is basically being applied here. And on a spool, basically, we have upward acceleration, which is ma. So basically, we know that, if you sum the forces on a spool in a vertical direction, you're going to have N minus mg is equal to ma. We're going to use small m basically for the spool. So we know m is going to be equal to mg plus a. Right, so the normal reaction that you're applying here is actually equal to mg plus a. So let us actually, quickly simplify that, and then here that force we know it's going to be mg plus a. So we're trying to find what is the maximum value for a, so that neither RA nor RB basically will exceed the value of 600 Newton. So, so what we know is how many equations do we have on this system that we have right now. We can sum the forces in the vertical direction. We can sum the forces in the x direction, but it won't give me anything. So we can sum the forces in the vertical direction. We can sum the moments. We have two equations and then two unknowns, which are RA and RB. So we should be able to find RA in terms of mg plus a and then big M. And then again, we should be able to find RB as a function of these. And basically, we make RB equal to 600, find what A is, make RA is equal to 600, and then find out what A is, and then we're going to use the least value for A. Does it make sense? So let us solve that problem. And basically here we know the moment R من هون لهون is equal to how much? This guy is equal to 0.5 actually, and this guy from here to here is equal to 0.75. And we know this guy, they gave us this value here, but I don't think we need this value, right? The vertical value. And then we know from here to here, it is actually equal to 0.7. So they kind of gave us a reference about that point, so we can use that point for our moment equation. So the first thing that we have to do is, and by the way, you can always, okay, so, all right, so let's do that. So we're gonna sum the forces in the vertical direction. And then what do we get out of this? We're gonna get RA, right, plus RB, right, minus, make it minus mg minus mg plus a is equal to 0. So we know RA plus RB is actually equal to, you know, the weight of this guy plus the weight of the smaller guy plus its acceleration. So, you know, it obviously automatically it is making sense. And then the next part would be to, we can sum the moments about a point here, right? We're gonna call it B. So if you sum the moments about point B, right? And I'm gonna use, this is my direction. Then what do I end up with? So I have RA is multiplying 0.75 plus 0.5 minus mg. So RA is in a counterclockwise direction. So clockwise direction, RA is in clockwise, mg is minus, so minus mg multiplied by 0.5 and minus mg plus a is multiplying 0.7, and then that guy is equal to 0. So RA is going to be equal to mg multiply 0.5 plus mg plus a multiplying 0.7, and this whole thing is divided by how much? 0.75 plus 0.5. So this is your RA. If you want to calculate RB, you can simply do this guy minus RA, or you can actually also find RA in another way, which is basically summing the moments about A, right? If you also sum the moments about A, we know that this guy is in equilibrium right now, and no matter where you sum the moments, basically the moments are going to be 0, right? So we can also actually pull the other equation based on that. So this is our RA, and RB is going to be equal to mg plus mg plus a minus RA, which is equal to mg plus mg plus a minus RA, I'm sorry, which is equal to how much? mg 0.5 plus mg, or mg plus a 0.7, and this guy is divided by 0.75 plus 0.5. So this is a value for RB. I'm gonna let you guys do the computations here. So all you have to do, like I said, is you are trying to find, you know, what is the maximum value for array so that neither this nor that basically is 600. So what you should do here is basically you put array is equal to 600, right? You make it equal to 600 and then you solve for a, right? And then you make RB equal to 600 and then you solve for a. And obviously you're gonna choose the least value, because if you choose a higher value, then one of them will be, you know, 600 and another one is gonna be more than 600. Okay, so this is how you basically approach these type of problems. Okay, okay, guys, so that is it. So again, here you can either use one of the equations to sum the forces. The other equation you can do here is basically you can also sum the moments about point A, right? And then that would actually give you the same result as you are doing here, right? So obviously one equation could be summing the forces in a vertical direction. Summation of the moments, you can basically sum the moments about two different points, right? And then this primarily works in the case of static problems, where you can use summation of the moments about two different points, right? And then you can use these two equations as separate, is because this whole thing is basically now it's turning out as a static problem, right? Most of the time, basically, you need to do one forces and then do one moments, right? Because these will definitely give you independent equations that you can use them to solve the number of unknowns that are contained in these two equations. Okay, very good. So now we're gonna go into another problem, and that problem basically is gonna go. to that problem. Let me share it. Okay, so here in that problem, basically we have this 2 kilogram slender bar supported by cord BC, and then released from rest at A. We need to find the initial angular velocity of the bar and the tension in the cord. Again, you know, every time you have a problem like that, you guys know what to do, right? The first step is to do a free body diagram, right? So let us do a free body diagram on that. And I think most of you has kind of get the hang of it, of, you know, what dynamics is all about. And really it's about having a good understanding of, you know, and then having a generic and fundamental understanding of how things should be done, right? Okay, so this is that, and then this is the rope, right? So we know that the force on the bar will always be equal to mg, right? And then this guy is at the center, right? And then what else do we have? We have a tension, right? So the tension is definitely going to be along the rope. Anything else over here? No, right? So that is it, right? So we have mg, and then we have a tension, and then, by the way, this guy is 30 degrees. And on the right side, what do we have? Again, this is a guy. We have mag, right? So even, you know, when you release that, you are going to have mag going downward. So I'm gonna actually put mag like that. And what else do we have on here? We actually have ig alpha, because when we release this guy, it will actually be rotated, right? And then you are going to have ig alpha. Okay. Okay. So how do we solve this problem? So how many unknowns do I have? I have t, right? I have ag, and then I also have alpha, right? And then that is my point B. Okay, so in that problem, can I relate Ag to alpha? Well, maybe yes, maybe no. Usually you can relate Ag to alpha in the case of rolling, right? But without friction, right? So it is rolling but without friction, and then we know if that, you know, circle basically, or it doesn't actually have to be a circle, it could actually be a rod here. We know if that distance here is r, we know, and that g, we know here ag is going to be equal to alpha r. Why? Because that thing is actually pivoted about that, right? Okay, so let's do that. So the first thing that I can do is I can sum the forces in the vertical direction, and then summing the forces, I'm going to get minus mg plus t sine 30 is equal to how much? Minus mag. You guys agree, right? So we have minus mg plus t sine 30 is equal to summing the forces in the vertical direction. I'm going to have minus mag. What else do I have? I can, for example, choose and sum the moments, right? I can sum the moments about the middle of that, right? Or I can sum the moments about point B and then see what happens. So if I, let me sum the moments about point B, and I'm going to use my counterclockwise as my direction, then I'm going to have mg. Let's assume the length of this guy is L. It would be L over 2, right? Assuming this whole thing is L, right? So mg times L over 2. How about t? Does t create any moment? No, right? Why? Because it is the moment arm here would be 0. How about on the right side? We are going to have ig alpha, right, plus mag multiplied by L over 2. All right, so from here, how do we go from here? So we cannot essentially relate. We have 3 unknowns. We have t, ag, and then alpha. And so far, we only have 2 equations. And for us to be able to make sense out of this, we actually have to have one more equation. And in this situation, basically, what we actually have to assume that ag is actually related to alpha in this case, and for us to be able to solve the problem. And we can basically assume that as soon as you release that, right, it is kind of like rotating about point B, right? So the minute where you release it, it is rotating about point B. And then we can, in that case, we can say the acceleration of the center of gravity is equal to alpha, right? The angular acceleration of the bar multiplied by L over 2. So by doing that, now I'm actually able to solve the problem. Otherwise, if this guy is kind of like, you know, falling vertically and then doing some random rotation on alpha, then it will be very difficult for us to actually solve that problem. Okay, guys, how about other accelerations? Do we have any other accelerations, by the way? Well, that force T is actually, it has a horizontal component, right? So we can actually have another horizontal component on we can say MAGX, right? But here basically we don't, MAGX is of no use to us, right? So that is why we're kind of ignoring that. So ideally this guy would be MAGX and then this guy is MAGY, but in this case MAGX is not helping us because we are considering the movement at the initial when you release it. If not, right, if you are considering the movement at any point other than the initial point when you release it, then this guy would be AG here would be like M omega square R, right? And then you would have to get R. So in this case, it suffices to just simply use MAG, consider the vertical component of the center of gravity's acceleration, and then we're going to use that, and then relating that to alpha, and then to solve the problem. So AG is equal to alpha over 2, so I'm going to come back to that second moment equation, and then I'm going to put mg L over 2 is equal to IG alpha plus, so AG is alpha over 2, so it's going to be M L over 2 squared multiplied by alpha. So IG plus ML over 2 squared, this whole thing is multiplied by alpha, so that is how we can calculate the angular acceleration of the block, or this thing, which is mg L over 2, divide that by IG plus ML square over 4. So now that you have alpha, you can actually get your tension, right? So let's call it 1, 2. So from 1, so T sine 30 is equal to mg minus mag, right? Where mag is equal to m alpha times r, right? So T is going to be equal to mg minus m alpha r divided by sine 30. And then I'm going to let you guys do the numbers over here. Crunching in the numbers and putting this on the final exam. Obviously, I want to see your overall solution, how you approached it, which equation, what did you assume, how you are relating your unknowns, whether you're using kinematics, whether you're using the friction, etc. Okay, guys, so I'm going to do one more problem today, and from this chapter, and this is a problem that I'm going to do, and then I'm going to keep that as a generic problem for you guys to be able to use it as you solve your assignments. And so this is a problem. So let's say you basically have a rod like that, okay, and the rod is basically sitting on the floor, okay. And I'm going to tell you that the coefficient of friction here is actually equal to mu k for kinetic and mu s for dynamic, right? And basically I have a rope tied over here, and I'm actually pulling on this guy with a force F. And I'm going to tell you that this guy has a length L, it has a mass M, and then G is acting downward, right? And what I would like to do is I would like you to find the acceleration of point A right here as a result of that force. So this is what you have. You have a bar, length L, mass M. It is, it is a thin, right? It is a thin rod, meaning it has, no cross-section area, right? And this is a force, and then this is your, the dynamics that we have. How do we solve that problem? What is the first step? Do a free body diagram, right? And just like what we said last time, so we have the force F, and mg is always at the center of gravity, which is in this case at the middle, right? We are going to have a normal force over here, and then how about the friction? So here we don't know what is the value of the friction, Mike. The friction will increase in response to F, right? Depending on the value of F, you are going to have a friction. If that friction is greater than mu s times n, it means that you are slipping, then you are going to update the friction by mu k times n. Some people will directly write the friction is equal to mu s times n. Guys, never write the friction is equal to mu s times n. The only time where you want to put the friction to be equal to mu s times n, when this is at the verge of sliding, right? If I ask you what is the maximum force or what is the acceleration of this, when this guy is on the verge of slipping, then you want to put the friction to be equal to mu s times n. Otherwise, you don't know what is the friction, and then you can solve for it. But what you should know is that the friction will always oppose the movement of that. So if this guy was, frictionless, as a result of this force, what do you think will happen? Right? Then this guy may rotate like that, right? And obviously it will move to the right, and then it will also rotate. So this is a friction, and then we don't know its value. On the right diagram, what do we have? We have MAG And then how about what do we have here in terms of we have IG alpha, right? So just like what we said last time, here we don't know the value for the friction, so it is an unknown. So for us to first of all solve the friction and then find out if it's greater than µs or less than µs, then what we have to do is we have to make some assumptions. And then what we said, we're going to assume that, I'm going to call this guy 0.0, we're going to assume that this guy is not slipping, right? Assume not slipping, then you find the friction, then you test if it's greater than µs times k, then friction, then not slipping is not an option and it has to be slipping, then we're going to replace it by slipping, and then what will happen here, ag will not be related to alpha r. So this is my ig alpha. So assuming not slipping, then I'm going to get this new relation that ag is equal to alpha times L over 2, right? And how do I solve for the friction in this case? I'm going to need to solve for the forces in the x direction, right? And I'm going to have F minus F is equal to how much? MAG, right? So your friction is actually equal to F minus MAG. And we know how many unknowns do I have here? Well, I have the friction as an unknown, and then AG is also an unknown, right? So this is my first equation, and then this is my second equation. The third equation is going to be summing the moments about point. So summing the moments about point O, what do you get? So you'll basically have, here we have AG, we have alpha, and then we have F. We have three unknowns, my AG, alpha, and then F. And then you have two equations. The third equation is going to be summing the moments about point O. If you do so, you're going to get F multiplied by L over 2 is going to be equal to MAG multiplied by L over 2 plus IG alpha, right? And we know AG is equal to alpha L over 2. So I think at that time, you're seeing that all these problems are basically similar, right? So if we're doing basically the same approach. So what is MAG? AG is alpha times L over 2. So alpha L over 2 square plus IG alpha, which is equal to alpha multiplied by ML squared over 4 plus IG. Obviously, the force is a known, right? You know how much force you're applying. So you can solve for alpha. Okay, so now we have alpha. We can get AG, which is equal to alpha times L over 2, and then we can solve for F. Right? F is going to be equal to F, which is known, minus MAG, which is alpha times L over 2. So this alpha, so F times L over 2 squared divided by ML squared over 4 plus IG. Now you want to test if that friction is greater than µs times N, right? So now is when we test, so rewriting that, so F is equal to F minus MF L over 2 squared divided by IG plus ML squared over 4, where here IG is equal to how much? Moment of inertia for a linear bar about its center of gravity is equal to ML squared over 12. So here you evaluate this. If F is actually greater than µs times N, it means that it is slipping. Therefore, F is equal to mu k times N, which is mu k times mg. Right? If F is equal to mu k times mg, then how the problem will solve? Then now Ag is no longer equal to alpha r, right? Now the linear acceleration of center of gravity is unrelated to the angular acceleration of the rod. And now summing the forces in x direction, it's going to give me what? So F minus mu k mg is equal to mag. So now we are solving the acceleration based on this directive. So you got Ag is going to be equal to F minus mu k mg over m. And we need to also get the angular acceleration of the bar. How do you get the angular acceleration of the bar? By summing the moments, right? Summing the moments about point O is going to give me, I'm going to sum the moments about point O. And I think I might have made like something silly here. So here I summed the moment about point O and I assume that that distance is L over 2. Let us actually keep it L over 2, but you know, you can obviously change, if you change that distance here, you know, F over L over 2 will basically update based on whatever that value is. So here, you know, assuming this guy is L over 2. Okay, obviously we're not doing anything, simply change whatever the moment value here is. So summing the moments about point O again, so F times L over 2, right? And this guy is going to be equal to how much? M Ag L over 2 plus what? Plus plus ig alpha, right? So this is the value for alpha. So what is the value for alpha? Now we can actually use this to solve for alpha. So alpha is going to be equal to f L over 2 minus mag L over 2 divided that by ig. So notice that what happens here is basically alpha could be positive or it could be negative, right? If f times L over 2 is actually greater than this value, so here, after you solve here, basically you replace ag by its value from here, right? Let us actually expand it one more time. I get to show you a small concept that is actually appearing here. So if I want to actually expand this further, I'm going to have f L over 2 minus mag. What is mag? So it's that, right? So m, this guy is dividing m, so I can basically remove m and just multiply this guy by L over 2. So I'm going to have f minus kmg, right, multiplied by L over 2. And then this guy is divided by what? This guy is divided by ig. Okay, so here what you really end up with is alpha is equal to fl over 2. Actually, it cancels out, so minus fl over 2 plus mu k mg times L over 2, and then this whole thing is divided by ig. So this guy is actually canceling out, so alpha is equal to mu k times mg L over 2 divided by ig. So here, basically, alpha is actually a positive, right? So it means whatever the value that I assumed for alpha is actually positive. So if I'm actually applying that force F, the bar will actually have to rotate to the right. It will not rotate in the other direction as a result of having this frictional force over here, right? So whatever value that, alpha here is positive, and if you actually increase the coefficient of friction, then the speed at which it basically, fall down is going to be greater, right? Okay. What I encourage you is you guys can, mess around with this guy and then see what happens if you had no friction at all. What do you think? You think this guy will fall to the left or to the right? Does the equation make sense or no? So these are things that you can work on your own, and in Friday's session, maybe we can also explore this a little bit further. But this is what you need to know right now in terms of the final exam, how you evaluate these problems, summing the forces, having the accelerations, and if you have this guy, all these numbers are obviously positive. None of the mass cannot be negative, g or L or mu k or whatever, right? So alpha has to be in the direction that you have assumed. So now you have ag and then alpha, then we can obviously get ap is equal to what? Ag plus alpha cross rp with respect to g minus omega squared rp with respect to g. Here we know omega squared is 0 when you basically when the force is just being applied. Okay, guys, so that really sums up what I wanted to discuss on this topic. Friday we are going to have a session where we'll also solve some problems together, and it will also be posted as well on Blackboard.